Morning. Let's get started. Can people hear me? Sorry, I was a bit sick last week, so I'm going to wear this. But if you can't hear me, just let me know. Yeah, so a couple announcements before we start. The second programming assignment is out. Everybody signed up. Either everybody signed up for their team last week, or you were randomly assigned into a group. If you were not, please let me know. And yeah, so the team contract is due on Friday, and then the actual assignment itself is due in about a month. So it's quite a lot of time. I don't think like if you actually start it and work on it regularly, it will not take 1 month, but we have a month anyway. So it's pretty relaxed. But if you, yeah, so maybe take a look. We'll do the lecture related to it on Wednesday, and you can take a look at the assignment, and if there's things you don't understand, let us know. And the same as the first programming assignment, it's better to start a bit earlier because the cluster will get quite busy near the deadline time, so it'll be hard to submit jobs. And yeah, so that's programming assignment. If there's any issues, no. Homework 2 is due Wednesday on caching. And the last one, we have an exam next Wednesday, just in class. So at this time, 9:30 to 10:45. I posted some practice exams on Canvas. So I changed the content a little bit from previous years. And so like previous years, they didn't include workspan and caching. So I added some exams also from a similar course at MIT that has questions on workspan and caching. They also have questions on other stuff, but we're not going to do that other stuff because we didn't do it in class. But the questions are there. And the format may change. Like the format of the practice exam may not be exactly the same as the format of the actual exam, but the content will be the same. You can bring one regular letter size crib sheet, front and back. You can put whatever you want on it, and you can just use it. We'll collect it after. So like we'll ask you just put in your test paper. So if you want to remember what was there, or if you want to keep it for later, just take a photo of it beforehand. Questions, concerns? People okay on programming assignment 1 that went in, I think, in the weekend? All good? Yes? No. The question is, are there any restrictions on what can be in the crib sheet? No, you can put whatever you like. It just has to be like in the size limit. Like you can put slides or like notes or whatever it is. Yes? Yeah, you can print it. It just has to fit on a physical regular letter size sheet. So like if you want to write it and print it, that's also fine. Yep. Questions? So today's topic will be the last topic on the exam. I think I said this last time, but the exam 1 topics we'll cover in the beginning. We did stuff like efficiency and speed up. Then we did workspan analysis, and then cache analysis, and finally we're doing prefix sums now. So for prefix sums, we will give you, like if you look at the practice exams, we will give you the bounds, like the theoretical bounds for the runtime on prefix sums. So you don't actually have to rederive those ever. The questions are more of the flavor, like how do you use prefix sum to solve something, rather than like how do you compute the prefix sum. You'll see it if you look at the practice questions. Questions, concerns about the exam, anything else? Okay. And there's a third homework coming today on prefix sums, so you could use those as practice questions as well. All right, so today we're going to do applications of prefix sums. This was pretty fun because it's just like a whole lot of tiny lectures combined into one. Yeah, so last time I said that prefix sums is maybe like one of these most fundamental parallel algorithms. And this lecture is about showing like many different cases in which you can use them. Okay, so if you remember from last time, what is prefix sums? It takes an input array x of length n, so it has n entries, x0, x1, up to xn. And you want to output an array y of n entries, y0, y1, up to yn minus 1, where the entry in y sub k is the sum, where sum is some aggregation according to an arbitrary operator. Well, not arbitrary. The operator has to be binary associative. For simplicity, usually we call this sums, but it could be like multiply, max, min, so on. It's just some aggregation from left to right. So the position at y sub k is the aggregation of all x sub 0 up to x sub k. And one thing to notice is that you want to compute every entry in Y. Like you're not interested in only computing the last one, which is just the special case of total sum, but we are interested in computing every single entry in this array. And we want to do it efficiently in parallel, and that's what we did last time, even though it looks kind of serial, because every entry depends, when you just write it in this recursive way, every entry depends on the one right before it. So like y sub k depends on y sub k minus 1. And it looks serial. An efficient serial algorithm would just like, you just loop left to right and you keep track of the sums. But as we saw last time, there are nice tree-like algorithms for doing it. Okay, so there are a lot of ways that prefix sum shows up. Some, we will not talk about all of these today, but some include, we will talk about adding n-bit integers. You can evaluate polynomials, you can solve recurrences. We will do radix sort. We'll kind of do this 2D parallel prefix and linked lists and others. So I guess the point is that it's not just limited to numbers, and it's not just limited to 1D space. You can do it in multiple dimensions. You can do it on data structures. You can do it on strings. Like it's not limited to 1D integer data. Right, so this is an example, the first example, the easy one. Suppose that we want to compute the Fibonacci numbers. And we did do an algorithm to compute Fibonacci, like when we were doing work span analysis. But like as some people noticed, that was inefficient because that was taking exponential time because you have to completely recompute you compute like a whole lot of subproblems repeatedly. And that was an illustrative algorithm, not an illustrative example of how to compute, how you should be computing fib, but how to do fortran parallelism. A better algorithm for fib, like if you do it serially, is just you do it left to right. Like you start with fib 0 and fib 1, and you keep combining them up until you get fib n, which is what you want to compute. And fib n plus 1 is equal to fib n plus fib n minus 1. And it seems like if you do it serially, it looks like there's dependency. You need fib n minus 1 to compute fib n, and so on like that. But you can do it with prefix sums. So using, so this is kind of like the flavor of how prefix sum problems go. You specify what your input is, like what is the shape of the data. You specify what operation you use as your associative operator, your binary associative operator, and then you apply the prefix sum, and using any black box prefix sum algorithm that we talked about last time, and then you say what is the output at each entry and how that corresponds to what you were trying to get in the final result. So for fib, in this example, the operation is multiplying matrices. The input is this little identity, or not identity, but like this little 2x2 matrix. And you can put the output vector like this and the input vector like that. And if you apply prefix on this thing, in the upper left entry, you can notice that these are the fib numbers. Does the shape of the problem make sense? Like this is what you'll have to do in the homework and in the exam. Not exactly this problem, but the way you set up the solution is like you say, what is the array of inputs? Like what is each entry in your input? Then you say, what is the operator I'm applying to this entire array? And then what is the output at each entry that I'm getting? So like in the terms of the previous definition slide is like, what is the X array? What is the Y array? And how do you go between X and Y by choosing which operator I'm going to use? Yeah. And this doesn't, so fib is one example of a linear recurrence, which is like the next term is defined by the previous two terms, or it doesn't have to be just any previous two terms. It could be any arbitrary linear recurrence expressed in this way as well. Questions? Another example is, so like that was just to compute fib, which is like, actually, in reality, usually you're just interested in fib of n sometimes when you're computing it, but you need to compute all intermediate results to compute fib of n for some given n. Another example of when you might want to use prefix sum is, this is for spatially manipulating some data. So this is like a very basic primitive called filter. And filter is, you're given a sequence A of length n, so like x of 0, x of 1, x to up to n minus 1, and you have an array of Boolean flags, b0, b1, up to bn minus 1. And you're only interested in the entries of A where b is 1 in that position. Maybe you did some pre-processing and those entries satisfy some condition that you previously set. And you want an output array where all the entries in the output array satisfy that condition. And you also want those elements in the output array packed left to right. Because like you can just get them easily, like scattered throughout the array, if you make an array of size n, like an output array, let's call it C, and you just you do like a for loop and you say if C of I, like you fill in C of I only if B of I is true. And your entry, the entries of C then will be all of the entries of A where B was true. And that is what we wanted, but it's not efficient because like if you want to iterate through those, you don't know where they are. So you have to iterate through all n, and there may be many fewer. So that's why I want to pack them left to right. And yeah, so the way that we do that is, again, with prefix sums. So the goal is we want to find the position left to right where all the correct entries of A are. And you want to do that in parallel. And so you can do prefix sum on B, where B is an array of 0 and 1. So then you do an exclusive scan on B, because it's not immediately right to do just an inclusive scan, because if you think about it, like if 1 is true, like the position of 2 is 0 in the array. But if this was 1, then we would just write the position as 1, which is incorrect. So we do an exclusive scan on the Boolean vector, and that gives us the positions that the correct entries of A should be in the output. It's called A prime. Does the problem make sense? Yes. Yeah, so let's just take one example. So we want to, so this is the Boolean array, and this is A. And we want, so like, here are the things that are true. So we want to put 2, 3, 1 in the front of an array. And so this is like 1, 0, 1, 1, 0. And so if you do a prefix sum on that, it'd be like 1, 0, 2, 3, 3. Or sorry, 1, 1, 2, 3, 3. But so if you just use that directly as the position, that would be wrong, because like this 2 needs to go in position 0. So you can't just use it. You have to be a little bit careful about like inclusive versus exclusive. But if you just looked at the first example, you would see like this needs to be in position 0, this needs to be in position 1. And if the minimum number is 1, then none of them can be in position 0. So it'd just all be off by 1. But the general idea still stands, which is that like you want to compact the true elements to the front. Mm-hmm. Yeah. So again, like this, you can do it serially left to right by you keep one pointer to the start of A, one pointer to the start of B, and you just walk them together left to right. And if you see true in B, then you write whatever is in A to your current. Oh, I guess you need another one in A prime, but you can do that efficiently in serial. However, you want to do it in parallel. So using prefix sums, we find the correct positions for the elements of A. Yeah. Oh yeah, this is what I was saying. So we do, this is the Boolean array, 1, 0, 1, 1, 0, doing an exclusive scan, 0, 1, 1, 2. And so like this is the code to do it. You just go over 0 up to n minus 1, and B prime, which is the prefix, after doing the prefix sum, is the array of indices that we're going to write A into A prime. So B prime is the index, A prime is the destination array that we want to write into, and then A of I is the actual element. Questions? Yeah. So yeah, this is called filter. And I think in the GPU world, it's called stream compaction. But this is just a really basic parallel primitive that you see often arise in algorithms. Like you have a bunch of data, you want to only keep the data around that matches some condition, and you want to put it in the front of an array for later processing. Questions? Yeah, so now, yes, please go ahead. For this one, it would be exclusive scan because we want to start in position 0. Because like these arrays are indexed by 0, so like 0, 1, 2, 3, and so on. And so we want to put the first element that matches true into the first position in the output array. And so like then the position of this thing would need to be 0 because the first thing is true. This is true in this one. So we need to put this one in the second position and this one in the third position. And basically what we're doing with the prefix sums is we're trying to calculate the position in the output that it's going to go in. Does that make sense? Mm-hmm. Yeah, so the question, exclusive scan is, so the definition that I showed on the first slide is inclusive scan, which is it includes everything up to and including, like when you're computing y sub k, that includes everything up to and including x sub k. Exclusive scan is just everything up to but not including x sub k. So like the first element is the identity, and then from there, you just accumulate everything besides the first one. Mm-hmm. Yeah. So both take the same runtime, and you can use like the same algorithms for both. But some problems need inclusive and some problems need exclusive. And you can do that. I guess here you can look at what should the first element, like what is the first correct answer, and if, and what is your input. So like 1 is true. So the first thing should have, but the first output position should be 0 because the arrays are 0 indexed. So that's how you know it's exclusive in this case. Good. Other questions? Cool. All right. So yeah, so that is filter. And so far we did Fibonacci, which is like a numerical application, and filter, which is kind of like sometimes like a spatial application, like you're trying to manipulate the shape of the data. Radix sort is kind of both. Like you want to manipulate the data around, but it's also sorting, so it's numerical in a sense. And okay, so radix sort is like this. You have an array that is unsorted, and radix sort is, it does sorting rather than comparison-based sorting. It does sorting based on the bits one by one, left to right, or sorry, right to left, from least significant to most significant. And basically the way it works is that starting from whatever bit you're currently on, you put all the bits in that position, or all the elements with 0 in that position to the left, and all the elements with 1 in that position to the right. And in the end, once you have gone through all the bits, the entire thing should be sorted, because that is what sorting is. Like the smallest one is like 0, 0, 0, 0, and the biggest one is 1, 1, 1, 1, 1. Does the high level make sense? So this is an example. We have this numbers 0, 1, 2, 3, 4, 5, 6, 7. And we start with the least significant bit. So like if these are the bits, 0 is the least significant, 2 is the most significant. Putting something something 0 before something something 1. This is just all the even ones, and this is just all the odd ones. So we would put all the evens to the left and all the odd ones to the right. And in serial, how we can do that is we can make one pass. We can make note of where all the evens are, and we count how many of them there are, and then we put them in the left and we put them in the right. Or like we put the evens in the left and we put the odd ones in the right. In serial, that required going left to right and counting up how many even ones there are. And that also requires, that requires counting up how many of them there are. But not only do you need how many of them there are, you also need to know where they are. because once you have that information, then you can move the elements in the correct positions to the left. And similar for the right side. And yeah, so then you do the same thing. Now we move on to the middle bit. So it's like whatever, 0, whatever, less than whatever, 1, whatever. And we keep the same original, so like this is stable in the sense that you keep the original relative order of the elements. So here, blue is the things with 0 in the middle bit, pink is the things with 1 in the middle bit, and you move all the things with blue left, move all the things with pink right. And you use this thing, which we computed in the previous phase as the input to that step. And then we just do the same again for the most significant bit. Now you can notice that all the elements are sorted, 0, 1, 2, 3, up to 7. And the reason that that works is because sorting is, in some sense, just ordering the bits. Okay. Is it clear to people how you would compute this in serial? Like the phases of course happen in serial, but the individual steps, like this pivoting, like kind of, not really pivoting, but like determining what goes to the left and what goes to the right. Do people see how you would do that sequentially? Like you could iterate through the input array. And does it make sense also like what the problem is if you parallelize it? Like, because the most straightforward way to do this sequentially is you would iterate left to right and then count up how many evens there are. And you could keep like a side array of positions. And if you had the side array of positions, then you could just scatter the evens directly into the left side and the odds directly into the right side. But generating that sequentially is one left to right pass. And we want to do it in parallel. Okay, so how do you do it in parallel? Well, we can do prefix sums. And this is sort of, in some ways, it's similar to filter. So in filter, you can kind of think of filter as like one, like if you just did a filter on the entire input array and the condition was that the thing was even, then you would pack all the evens into the left side. But you also want to pack the odds into the right side correctly as well in the same pass. So we're in some sense going to do like two types of filter simultaneously. So this is how it goes. This is the input. And so this is some array that tells you whether or not the thing is odd. So 1. So this is kind of like filter a little bit. So 1 is in this. So we put a 1 in this array if the thing is odd, and we put a 0 if it's not odd. Then we keep a symmetric array that's just 1 if the thing is even, and 0 if the thing is not even. And our goal, again, is to put the evens in the left side and the odds on the right side. So if we had this evens array, which is just a Boolean array, and we performed a filter on using this input array, then we would get all the evens into the left side. But we can't just directly do that in place because then we would overwrite some of the odds, and that would be a problem. So we need to keep track of the odds as well. Yeah, and then even positions is just like the same filter that we did, which is an exclusive scan on the evens. And pink is oh, I guess I did the colors wrong, but it should be like 0, 1, and so on. And then, yeah, so then we keep track of how many evens there are in total, which is the difference in the position, which is the start of where the odd elements are going to begin. And this is an array of the total indices. And the way that you get the odd positions is by adding the number of evens plus the index array minus the even position. So this is how many evens there are up to this point. This is the total number of evens, so like the start position of the odds, and this is the index in the total array. And the goal of this is we have found where the evens are starting, left to right. We want to find where the odds are starting, kind of like starting from the middle position and going from there. So it's similar to this filter type thing, but rather than the start position being in the very beginning, the start position is where the evens have ended. And then finally, in both these arrays, this one and this one, are the correct positions for both odd and even, and you just need to determine them correctly. And you know that because you know which ones are even and you know which ones are odd, so you can use these as masks to get a final output array of positions. And finally, after you have this output array of positions, you use that to write, you have this input array of actual numbers, and you want to scatter it left to right, even and odd. And the reason that we wanted to do all this is because you can parallelize the intermediate step. So we did the entire intermediate step at prefix sums by doing position manipulation. And then this is the first step of the entire radix sort, which is that you start from the least significant bit and you put the things with 0 in the least significant bit to the left and the things with 1 in the most significant bit to the right. Questions? This thing? You can just keep, how do you know that there's a total of them? You can keep one extra position in the output, and then yeah, and then you just keep track of it at the end. Question. I guess you can get it by you keep one extra position, and you using the exclusive scan, you can get everything up to here, and then you just add this one and this one together. Question. Other questions? Okay. Yeah, so that is radix sort. And radix sort is nice because like the steps are parallel, and it is nice because also the steps are in some sense independent of the input size. Like the prefix sums are not independent of the input size, but independent of the input shape. Like the prefix sums are always the same, the scatter is always the same. And so it's really nice for data parallel architectures such as GPU, where things prefer to have the same operation. So this is the algorithm, the pseudocode. This is a lot of text, but basically how it works is that you go from, this is 0 up to b minus 1, which is the number of bits. And we do the bits least significant to most significant. And then we basically do what I just showed in the previous slide, which is we keep this flags array, which is keeping track of whether the current bit is odd or even. And this is the inverse. And then we just do this scan, these bunch of scans to find the position. And then this final assignment is assigning the final position according to the positions found in the prefix sum. So if we analyze the work and span of this thing, there are b iterations of the outer loop. Each step in the inner loop is at most order n. Like if we go back here, each one of these steps is linear in the length of the array. This one this one is easy to do in parallel. You just check in parallel whether the element is odd or even, and you can write in 1 or 0. The prefix sum is linear time, and these calculations are also linear time because there's one calculation per element. So the total work, there's a constant number of these steps. The total work is order n, and there are b rounds of this, so that's b times n. In terms of the span, it's hard to parallelize the outer loop because we have to go bit by bit, but so that's b, but there's log n span for each of the steps in the inner loop because it's either this parallel assignment or scan, which are both log n span because it's just a parallel 4. to the total span, you multiply them, that's b times log n. So the takeaway here is this is, of course, more complicated. Like the inner part is much more complicated than the serial version. But if you're not careful, then you may end up serializing the inner part, like stuff like the prefix sum and the assignment, the initial assignment of finding this condition, like odds and evens. Those should all be parallelized to maintain the efficiency. Mhm. Could you? Oh, is the question like, could you start from the most significant bit? Um, start from the most. Maybe. Let me look into it and get back to you. From a programmer perspective, it's totally fine. Like you just run the outer loop in reverse. So like you could just run the same inner part. Is there any? Oh, like you don't know how many bits there are? You can calculate how many bits there are. Like you can take the max. Can't you? Like, so to find the maximum element, you just take the max over the entire array, and you need log of how many of whatever that is to find the number of bits. Can do it more significant first. Let's go back to this. Maybe. Let me get back to you. Thanks. Other questions? Yes. Oh, no. They do not have to. The input elements do not have to be continuous. Or, sorry, yeah. There can be duplicates. There can be, the elements can be all over the place. But in the end, they will still be sorted, no matter where the elements are, they will still be sorted according to their bit position. Like in any sorting algorithm, in the end, they end up sorted according to the bits. Yeah. Other questions? Okay, so that is radix sort. You can also use prefix sums to add integers. So for integers, suppose that we have two n-bit binary numbers, a and b, and we want to compute the sum of them. And the way that we compute the sum of them is bit by bit. So like a0 plus b0, a1 plus b1, those give us like the bit positions of c, which is the output integer. And the way that you compute, this is like, like when you add numbers, like we learned in elementary school, the way you add numbers is right to left, and you may have to carry over some numbers from the different columns. And in base 10, like you carry over something like base 10. In base 2, you carry over either 0 or 1, where it's 0 if these two elements don't. So like for addition, there's this carry array, and the carry array, there's two notions. One is carry in and carry out, which is just the way you regularly do addition. Like carry in is whether you get a 1 propagated from the previous position, and carry out is whether you yourself are going to get a 1 out to the left. And one example, like a carry in, would be like if you are like a carry out, like let's say you're adding 1 and 1, then that would move 1 to the next position. If 1 and 1 were to your right, then that would move 1 into you as well. So like if to your right was 1 and 1, and you are 1 and 0, then your output would also carry out a 1. And so we can add these numbers just right to left. Like we compute the bit sum, we know what the carry in is from the right, and we know what the adding all those three things together, we can know what the carry out is to the left. And so to add integers, we can do it right to left, just sequentially, but we want to do it in parallel. So this is the pseudocode. We have, so we want to compute the sum, a plus b, which is this bits. And so in the initial one, we had n bits, and the sum could possibly be n plus 1 bits. Just like you need n plus 1 bits if you add two n-bit numbers. So the total sum could be like 2 times whatever that thing is. And we need 3 parts. We need A and B, which are the input numbers, and we need C, which is this carry bit array. This carry bit array is like what I was just saying. It depends on the input numbers, just like regular addition, right to left. And this is how we can compute the sum. So from right to left, we can use the sum, which is the actual position there, or the actual thing in the output, is A of I XOR of B of I, XOR of C of I minus 1, which is the carry in. So the initial carry in at -1 is just 0. So there's a 1 in the output bit position if there's 1 or 3 ones that go into it. Otherwise it's 0. And to compute whether there's a carry in, there are 2 cases. One, the simpler one, is if both A and B are 1. So that would, like you add them together, and they have to come out. Another case is if either A or B are 1, and you get some carry in from the right side. So this is an example, A and B. C is the carry, and S is the sum. So 0 plus 1, carry in is 0, so that's 1, because there's 1, 1. And there's no carry out, it's just 0 plus 1. And 1 plus 0 is also 1, no carry out. Then you have 1 plus 1. So 1 plus 1 is 0 in binary, but then there is a carry in to the next one. And then that's 0 plus 1, and the carry in is 1, so that will give you 0. So there's 2 1s, and so on like that. Is the problem clear? And is it also clear like how you could just iterate right to left and compute these? So like in your hardware, this is a thing that your hardware needs to do to add numbers, like any adders or something like that. Mm-hmm. Yeah, so we're gonna get there. Yeah. So this prefix sums are under carry adder. Yeah. And so so this is the problem, and we want to, in hardware it's called like making adders, and we want to compute all these. So we can always compute A and like whatever A and B, A of I and B of I, any computations related to that in parallel, because we have those up front. But we don't have C of I up front, and it depends, both the sum and the carry depend on C of I minus 1. So it looks like it's sequential, but again, we can use parallel prefix to get around that. The goal is that we want to compute all the carry bits using parallel prefix. Yep. And so the way that we're going to do that is to split the carry bit into cases that we can compute through parallel prefix. So there's 2 cases. One is generate, which is this column is going to do carry out whether or not the carry in is 1. And that is the case where both of these A and B are 1. The other case is propagate, which is if there's 1 that is coming into you, then there will be 1 that is coming out of you, and that is A or B. And this is just how you compute the carry bit at position I, which is it is going to always generate, or it will only push 1 out if 1 gets pushed in. And so then you can do it. This is carry look ahead addition. You can do it via parallel prefix. So now we express the carry bits using this G and P that we just defined. This is G or P and Ci minus 1. But Ci minus 1 can be expressed in terms of all the previous iterations. So this is the base case. G plus is or, and multiplies and in this notation. So P times C negative 1, and c of 1 can be expressed using the same type of expression with c of 0 here, but we have an expression for c of 0 already. So we just plug in this thing for c of 0 into here. And we can do that all the way down. So like we would express c of 2 in the same way, like g sub 2 plus p sub 2 times c sub 1. But we have this for c sub 1. And c sub 1 can also be expressed in c sub 0. And we have c sub negative 1, that's just 0. Because there's no carry in the very beginning. And so you can express all of these in terms of the most basic thing that we have initially, which is c sub negative 1, just by unwinding the recursion. And that is something you can do up front. Like if you know how many bits there are, like with a fixed bit width, which is what we have in hardware, then you can up front unwind this entire recursion and build hardware to compute this in parallel. Yeah, from a math perspective, you can also express it with multiplication. By unwinding the recursion up front, I mean, if you know how many bits there are, you could write c sub I for all of those I, like unwinding it like this, like substituting in the expression that you have for the previous one, which substitutes in the previous one for that, and so on. And then, so in the end, everything is going to be defined in terms of these g and p and c negative 1. And that is nice because g and p don't depend on c. Like they just depend on a and b. So they can be computed all independently in parallel without any prefix sums or anything like that. Question, yeah. So just to clarify, the goal is we want to express every carry bit in terms of g and p, which only depend on a and b, and c negative 1, which is just something that we have up front. Yeah, and you can also express it with Boolean matrix multiplication. But yeah. And this is called carry look-ahead addition, and that is used in all computers today because computers need to add integers quickly. Questions? Yeah, so it comes from the 1800s, but nowadays it's used in all modern hardware, dad numbers. So those are all number applications, like numerical applications, sorting, carry look ahead. You can also use prefix sums on strings. One way that you can use it on strings is in something called lexical analysis. So lexical analysis is something that every compiler has to do when you process a program, which is you break up the program into tokens, which are like keywords, and it interprets. So your program is just one long string of characters. And in the compiler phase, you need to break up these characters into tokens, and then you need to process the meaning of those tokens. And those tokens bring you, in some sense, you can think of it as every program starts from some initial state, and the tokens bring you between different states. And yeah, so if you have a regular language, which is something that you may learn about in your theory of computation class, you can represent it with a finite state automaton, which is just a series of states, and there are arrows between the states, and the tokens bring you between the states. And like the different, so this is an example, like if x is at most n, then print this thing. And the compiler would just break it up into different tokens based on the syntax of the language. And so we want to, like if you run your program, or if you run the compiler, then the tokens will tell you between which states we're moving. And one way, of course, to run that is you just run it left to right. Like you have these tokens, you read them left to right, and then you eventually get to some end state. If you want to do it in parallel, you can do something like prefix sums on the state table. And this is similar in some ways to carry look-ahead addition, which is basically that we're going to unwind the recursion up to something that we have in the initial condition. Yeah. So the way we do it is we have this table initially, which is it takes some characters. it has some initial state here, and it moves into some new, like based on what state you're in and what character you read, then it moves to some new state. And you can, of course, read this character by character and move between the states. Instead, basically what happens is in lexical analysis, you can compute prefix sum on this thing, basically. And so rather than each step being one character, each step, when you do it the entire way, you want to express the entire. Basically, what happens is that you use the array to make a log where the index is the initial condition and the state transition is the entire program. And the way you can do that is by composing the different tokens using parallel prefix. And then from there, so basically you do parallel prefix on the entire table, and you have some initial state, and you just use the initial state to index you into the final state. Questions? So this, we're not going to do a lot with the string prefix sums, but it's just an example to show that prefix sums doesn't always have to be on numbers. The high level idea is that you kind of compose these intermediate steps. Mm-hmm. Yes, so this is like the old state, and this intermediate part is the characters that you can read, and then this is the next state that this character moves into. Mm-hmm. Yeah, and so if you compose two of the characters together, then that would be like if you had read two of those characters at once, then what state would you be in after that? And basically, you just keep applying this to the entire program. Mm-hmm. Question? So going back to numbers, another way that you can use prefix sums is in some, this is a modified version of prefix sum called segmented scan. And you have an input, which is some value array. You have a flag array that tells you, basically, like you have an input array, and the input array is in these logical chunks. But the flag array tells you where the chunks start. And you want to compute prefix sum within each of the chunks. And you often may want to use this. For example, like there's a common problem that people have spent a lot of time optimizing called sparse matrix vector multiplication. And this is one way that you can do sparse matrix vector in parallel if each of these is one row of your sparse matrix. So this is just a variant on prefix sums where you don't do prefix sum over the entire array, but you do prefix sum just over segments of it. And the way that you do that is basically you run the algorithm for doing it over the entire array, but you just kind of reset it where you see 1 at the end of the segments, or at the start of the segment. Okay. So this is a classic example of how you can use prefix sum, which is in image processing. It's called computing the summed area table. And it's like one of these classic problems in image processing. So the goal is that you have an input of a 2D grid, and the 2D grid has some integers in the positions. It could be pixels, probably for image processing. And the goal is that we want to compute the sum of the elements in any arbitrary rectangular square of the grid. So it is easy to see how to do it with prefix sums if you are only interested in rectangles that originate from this upper left corner. Because like you have this 2D grid, you can do a horizontal prefix sum in every row. You can do a vertical one then along every column. And every element in this output 2D grid is now the sum of elements starting from the top right corner in that rectangle. However, we are interested in the sum in every arbitrary rectangular grid. We want to be able to answer this kind of query in order 1 time. And so like if you did horizontal and vertical prefix sums, then you would easily be able to answer queries of the form rectangle starting at this upper left corner with lower right corner in any position of the total sum in that kind of rectangle. But to answer arbitrary rectangles, we can use inclusion-exclusion. The way it works in this picture. So let's say we're interested in this purple box, sum of elements in this purple box. You add in the sum of elements in this whole big yellow box, but now we need to subtract some stuff out because like some stuff is not in purple. So we would subtract out this blue. Yeah, we subtract out this blue, which is not included. We subtract out this green, which is not included in purple. But notice that we subtracted this twice. And so we need to add back in red. So yeah, so that is inclusion exclusion. And so we add in the entire thing, we subtract out 2, and then we add back in. Yeah, and using that, with this preprocessing, just 2 passes using prefix sum, you can answer arbitrary queries, arbitrary rectangular queries. You just need to know the 4 corners, and then you do addition and subtraction on the corners. Questions? Yeah. One thing that I didn't mention is that this requires you to have an inverse. So for addition and subtraction, that makes sense. And you can also, like multiplication has division as the inverse, but not every operator, or sorry, not every binary associative operator has an inverse. So if you're interested in doing this for algorithms without inverse, it becomes a bit more complicated. It is possible, but it's not so nice like this. Yeah, another way to use prefix sums is in list ranking. Yeah, so list ranking is this classical problem that shows up in a lot of tree algorithms, basically for jumping elements in a tree. And the problem is like this. You have a linked list, just singly linked list, and you want to determine the distance from every node in your singly linked list up until the end. So this one, in this example, 0 is distance 0 from the end. The thing that points to 0 is 8. This has distance 1 from the end. The whatever is going to 8 is 7. This is distance 2 from the end. This is distance 3 from the end, and so on like that. So in memory, like the nodes of your linked list, maybe wherever they are, but you want to find the position. You want to find the distance from the end. And so this is what we would output in list ranking. And in serial, you can do this in order and time, because you can start, if you have the backwards pointers, you could start from the end and go backwards. If you don't have backwards pointers, you can make 2 passes, because it's, yeah, so I said it was singly linked, so you don't have backwards pointers technically. You can make 1 pass through the entire thing, which tells you the total distance. And then you can just keep track of a counter as you go. And then the distance is just the total minus the counter, if you don't have the back pointers. So that's how you do it in serial. You make 1 pass through your linked list, you keep track of a counter, you keep track of the total at the end, and then you can invert the counts at the end. Okay. Let's assume that we can write this linked list in an array, and we have n nodes, and we write them in an array specifying their order. So the array looks like this. If you're not initially given the linked list in this format, you can make it into this format with 1 pass through the whole thing. And the entries in the linked list array are just the number pointing to which one is next. Yeah. So every entry in this list is a pointer to the index of the successor, or 0 if it's the end. And we want to output a list R of the same length containing the distance from the end or the rank of every element. And the reason for this array format is just that it's easier because in the pseudocode, it's easier to manipulate arrays rather than do pointer traversal. But we can put the entire linked list into array format through just one pass through the entire thing. Okay. So one classical algorithm for list ranking is called Wiley's algorithm. And the way it works is kind of like in this picture. Initially, we have this linked list like this. And in the first stage of the algorithm, we hop. So in the beginning, it's like distance 1. And then in the next step, we skip over things that are distance 1. And then we just, now everybody is pointing to something that is distance 2 from itself, rather than, except for the last one, which doesn't have anything from distance 2 from itself. And the way that you can do that is just like you set your next to what was previously your next. And if you do that in another phase, then you will get things that are distance 4 from you. Because if you set, like in each round, you set every linked list entry has like a pointer to next. In the beginning, that is distance 1. In the first phase, if you set your next to next, that is now distance 2 from you. But in the next phase, if you set your next to next, it will be distance 4, not distance 3, because everything in the first phase also converted to distance 2. So it'd be like 2 plus 2. Or something like that. So this is the pseudocode. This is just the initialization. And the parallel fors are like this. So for 0 up to log n, where n is the total number of entries that there are, we do this assignment. So this parallel for up to -1. This is just saying, this is what I was saying with the next assignment. Like L is initially the list of successors. And so like this is successor of successor. And R is just L of I in the beginning, where L of I is the successor. And then finally, R of I is R of I plus temp of I, which is this thing. And then L of I is temp 2, which is successor and successor. And the reason that we need these temps is we don't want to initially just overwrite L, because we kind of need that. The pseudocode is a little confusing, but basically you can think of it spatially like this. That initially you point to distance 1 from you, the next phase you point to things that are distance 2, next phase you point to things that are distance 4, and then 8, and so on like that. That's why there are log n rounds. Okay, so we are interested in computing the work in the span. Maybe we can start with the work. Good, yes. How? Yes, exactly. Good. So the outer loop is log n. These inner ones, like to do the work, you just ignore the parallel part. So this is linear, this is linear. So the outer one is log, the inner work is linear. So that's n times log n, or sorry, I guess log n times n is n log n. And the span? How did you get log of n? Sorry, who was it? So let's do, so what is the span of these 4 loops? And how many times do you have to go around? Yes. Yeah. So good. So the total span would be log squared, because the inner 4s are log each, but you have to do them log times. You just... Oh, sorry. I should fix that. It's log squared. It's log NPRM, but I have to fix it. It is log squared. This is not work efficient because initially in serial, you can do it in n time. You just make 1 pass through the entire thing, but this is n log n. So it's slightly work inefficient because there's an extra log factor on the work, but the span can get down to log rather than linear for the serial version. I'll fix this and upload it. Yeah. Sorry? Yeah, it's a good question. So the question was, why would you be interested in this if it's not work efficient? Um, because it is parallel. And it's not, so yeah, it's not ideal that it's not work efficient because we want work efficient algorithms, but log and factor is not that much in terms of the work. So sometimes we're able to accommodate small log factors. Yes. Does it still work for this? Yeah, this is just the array is just like is it just a different representation of a linked list? Yeah. Yeah. So it's a good question. So the array is generated by pointing to the successor. So you kind of like, yeah. So like this is just a index to the pointer. Sorry, each entry is a pointer to the successor, and yeah. So like here, like for example, this is 4 pointing to this one. Yeah. Thanks. Mhm. Yeah. So if you remember, like the clouds that we had, like in the beginning, when we were doing work span analysis. So uh, for the clouds, if something is happening in parallel to each other, then the span is max. And if something is happening one after the other, then the span is added. And so here in this case, the span is added because this 4 is serial. And then there is an inner parallel 4, 2 inner parallel 4s. This is log, this is log. Yeah, so one way to see it is maybe just ignore the outer 4 for a second. And then just think about these 2 parallel 4s. This has span order log. This has also span order log. So you would add them up, and that's, again, order log. And then we see, okay, well, this is order log, so how many times do we have to do it? And we have to do it log times. Yes? Why the span? Um, because the span of each of the inner 4s is log n. And so this one is log n, this one is log n. And so the total span is how many times you have to go around for these. And so you have to go around log times, so that's log squared. Huh? That's a question? So you could think of it as like log n, this thing. One iteration is log n, then the second iteration again is log n, and then how many iterations are there? There are log n iterations. Cool. Other questions? Yeah. So I think I have time for maybe one more. So this last one is tree accumulation, which is an operation that we are interested in doing on trees. And yeah, so we have these vertices, v1, v2, v3, and so on. And each of these has entries x1, x2, x3, stuff like that. There are 2 kinds of accumulation that we might be interested in doing on trees. One is called upwards accumulation, which is for a given node v, we are interested in summing all the numbers in the subtree. So for this example, in v sub 4, this one. We want to sum up all of these numbers, so x4, x7, x8, x9, x10. And then, oh yeah, so we're interested in upward accumulation. And for these problems, we want to do it for all the nodes. So of course you can just do it for a single node, like we would just start from x sub 4 and do like a binary, do like a breadth first search down. But if you want to do it for all the nodes efficiently, then we need to do some kind of fancier algorithms. And the inverse of that is called downward accumulation, which is for each node v, sum all the numbers in the ancestors counting itself. And upward accumulation also is counting itself. So for v7 here, the ancestors starting from ourselves, x7, x4, x1. And we can compute both in theta n time and serial for both upward and downwards. The way that we're going to do it is by starting with the Euler Tor, which is, people remember from graph theory, basically the way we search that we start from the root, and then we do, we just do like a, yeah, just like a left to right traversal reorder, I guess. You recursively visit the left all the way down, you visit the right, and then you visit the center. And so this would be the Euler Tor here, v1, v2, v5, v2, v6, v2. The thing to notice here is that we visit we can visit the same vertex multiple times, like, but you visit it an even number of times. You come in and then you come out. Assume for a second that we have an algorithm to compute this in parallel. We're going to use it to compute the upward and downward accumulation. So for the upward accumulation, here's how it works. You write the Euler Tor, just left to right, in terms of the vertices visited. And the length of the Euler Tor is 2n minus 1. And in the upward accumulation, remember what we wanted is for every entry, or for every vertex, we want the sum of itself and all of its descendants. And so from an Euler Tor perspective, how can we do that? Well, the first time we enter a node, then between the first time we enter a node and the last time we exit the node is the traversal of the entire subtree. Because that's how the definition works. You enter a node, you explore the entire subtree, and then you come back out to the parent. And then you start like the next sibling, so on, down there. And so basically what we want to do is we want to query the sum between the first occurrence and the last occurrence in the Euler Tor. And the way that we can do that, for the first occurrence of any vertex, we put x sub I, and otherwise we put 0. So we may visit it multiple times, but for the first one, we add in its contribution as x sub 1. And then we compute the prefix sum on that. And we want to know when is the first and when is the last. And if you subtract between the index of the first occurrence and the index of the last occurrence, then everything between that is the contribution from its subtree. So. Okay. So that asks the question, how do you know if an entry is the first occurrence? And ideally, we would like to find it in parallel because we want to compute this array in parallel. Give you a hint. You can, let's say that you can look at the Euler. You can look at the Euler Tor, like you can look to your left and right entries. Mhm. Uh-huh. Yeah. Uh, I think I said something slightly more precise than that, but the general idea is the same, which is if yeah, the thing that is to the left of you, if it's the parent, then you know that you're the first occurrence because you had to come in from the parent. But because it's ordered from the top down, another way to do it would be if the thing to the left of you is less, because the thing to the left of you would be the parent. Mhm. Does that make sense? Mhm. Yeah. Yeah. So that was upward. And then downward is similar. It's a bit different. So remember, downward is that we want to sum up ourselves and the ancestors. And the way that we're going to do that is for the first occurrence of a vertex, we put x sub I, and for the last occurrence, we put negative x sub I. And the reason for that is that when we first show up, then that is our contribution. But then after the last occurrence, then we are exiting, and then we're going into the higher parts of the tree. And so we are no longer contributing to the downward accumulation. And so that is why this negative x sub I is here. And then now just in reverse, we want to find the last occurrence. And how do we do that? Mm-hmm. Mm-hmm. Yes. Is that what you were going to say? Yeah. Good. Yeah. So yeah, just look to your right. If it's your parent, then you're the last occurrence because you're coming back up out of it. So this thing about like looking to the left and looking to the right, it's not really about, it doesn't require like any parallelism, but it is something that is motivated by parallelism because it's something that we want to check independently. But this is just like, I don't know, graph manipulation tricks. Yeah. And so for the downward accumulation, we want to say that the prefix sum is up until the final position. This is not totally right. So if you check the leaves, for example, x sub 5 here, well, it's right for x sub 5, but it's not right for x sub 6. Because here, for example, x sub 5 would be the prefix sum up to this point. So it'd be like 1 plus 2 plus 5, which is fine. This is this. But if you look at 6, then it's like 1 plus 2 plus 5 plus 6, which is not right. We want 1 plus 2 plus 6. And so the way we can fix it is we put, for the internal nodes, we follow this same scheme, x sub 1, negative x sub 1. But for the leaf nodes, we just put 0. And then we can change the final result calculation. For the internal nodes, the prefix sum will work because now the leaves are not included in this array. For the leaf nodes, we just add it in at the end. Keep track of that. I think I'm out of time, but I have one summary that I want to say. We're just going to do that. Anyway, so hopefully I've convinced you that prefix sums are everywhere. And now that you know about prefix sums, maybe they will appear every day in your lives. They have applications across integers and strings. They are not limited to 1D. Like the actual algorithm is 1D, but like you can run it in multiple dimensions, just horizontally, vertically, in arbitrary dimensions. The algorithm is one of these canonical parallel algorithms that looks really serial at first because it has this dependency all the way down the line, but they do admit nice, efficient parallel algorithms. And when you solve the problems like in the homework or in the exam, the way that you do it, you specify the operator, so like add, multiply, so on. You specify what is the data in the input, you specify what is the data in the output, and then how to use the prefix sum to get from the input to the output. Thank you.